All right, welcome to this explainer. I'm so glad you're here. Let's just jump right in. Imagine you're a ninth grade student in Pakistan, sitting at a perfectly neat study desk, sunlight streaming in, notebook wide open, and I'm right here with you at the whiteboard as your guide. Today, we are cracking open the incredible states and structures of matter, looking at how the entire world around us is built, from everyday stuff right down to the hidden architecture of atoms. We're going to be using this beautifully structured textbook page as our foundational map today. It's a fantastic look at the states of matter and phase changes, and it's going to help us unlock some pretty mind-blowing phenomena where elements literally change their entire identity just by changing their shape. So here is our quick agenda for today. 1. Branches of everyday chemistry. 2. The magic of allotropy. 3. Carbon's 3 unique forms. 4. Sulfur's dual crystal structures, and 5. Coal versus diamond. Starting with Section 1, Branches of Everyday Chemistry, Seeing Science Everywhere. Chemistry really isn't just about people in white lab coats swirling bubbling liquids. It's literally everywhere. Digesting the lunch you just ate? Well, that's biochemistry in action. Watching the bright explosions of fireworks? That's inorganic chemistry. We can zoom way out to study entire ecosystems for environmental chemistry, or zoom in on the rate of a reaction and plasma for physical chemistry. And if you're measuring UV spectrometer wavelengths, yep, that's analytical chemistry. The whole world is basically one giant lab. Moving right along to Section 2, the magic of allotropy, the rule of structure. Okay, so let's look at the actual definition from our source material here. Allotropy happens when elements exist in more than one structural form, exhibiting quite different physical and chemical properties. Basically, it means nature can take the exact same set of atomic building blocks, rearrange them, and give you something completely new. It's kind of like magic, honestly. So the golden rule to remember here is same element, different structure, different properties. How the atoms are arranged is literally just as important as what those atoms actually are. It's like taking a pile of bricks. You could build a flat patio, or you could build a towering chimney. Same bricks, totally different result. A super familiar example from our text is oxygen. It has 2 main allotropic forms. Form 1 is O2, which is the standard oxygen you are breathing in right at this exact second. But if you tweak that structure just a tiny bit and make it O3, you get ozone, form 2. Same element, but one keeps us alive on the ground, and the other forms a massive protective shield high up in the atmosphere. All right, Section 3, Carbon's 3 unique forms, the ultimate shapeshifter. Carbon is absolutely the ultimate shapeshifter. According to our textbook, it takes 3 distinct forms. First, you've got diamond with its giant macromolecular structure. Then there's graphite, which is just a layered structure of hexagonal rings. And then we get to the really wild one, Buckminster fullerene, or C60, which is made of actual spheres of atoms arranged in pentagons and hexagons. Let me read this quote directly from the text because it's fascinating. The fullerene structure is unique in that the molecule is not charged, has no boundaries, and has no unpaired electrons. They have a cage-like structure. I mean, just picture that. A microscopic, perfectly symmetrical, uncharged cage made entirely of carbon atoms. It basically looks like a tiny soccer ball. And because of that specific spherical C60 shape, its properties are completely bizarre. The text notes it's stable at high temperatures and pressures, it's covalent, and it's actually soluble in organic solvents. But here's the crazy part. Unlike a hard diamond, this form of carbon is soft, has a low melting point, and absolutely cannot conduct electricity. All of that just because it's shaped like a cage. Next up, Section 4, Sulfur's dual crystal structures, a tale of 2 lattices. Carbon definitely isn't the only element pulling this trick. Sulfur exists in 2 crystalline forms, rhombic and monoclinic. Now, both of these are made of the exact same S8 molecules, but in rhombic sulfur, they form a rhombic crystal lattice, while in monoclinic, they form a monoclinic lattice. That simple shift in geometry completely changes its physical form, though our source does note that the rhombic form takes the crown as the more stable allotrope under standard conditions. All right, Section 5, Coal versus Diamond, a real-world contrast. Let's put all this into perspective with a real-world comparison from our source table here. Look at coal versus diamond. Coal is this messy, combustible, sedimentary rock, a mix of carbon with hydrogen, sulfur, oxygen, and nitrogen, used mostly to generate heat and electricity. Then you have diamond, pure carbon, a perfectly rigid 3D crystal lattice. It's incredibly hard, completely transparent, has a high refractive index, and is used for everything from fancy jewelry to heavy-duty industrial cutting. Same foundational element, entirely different universe of uses. So, taking a step back and looking at our complete lesson plan from the textbook pages today, we've really covered a lot of ground. From the branches of chemistry that explain everyday life to the profound, almost magical power of atomic arrangement. You've done an absolutely awesome job tracking with these concepts at the whiteboard today. As we wrap up this explainer, I want to leave you with a thought to chew on as you close your notebook. If nature can hide a sparkling, indestructible diamond inside the exact same basic element that makes up the soft, crumbly tip of your pencil, what other hidden forms of matter are just waiting out there to be discovered? What else can we unlock just by rearranging the building blocks of the universe? Keep questioning, keep studying, and I'll catch you in a next explainer.